solution of the class of universally quantified constraints. And okay, so I guess you have around 25 minutes.
Thanks for introducing me. So I'll try to give you some more concrete problem that I want to present on this quite abstract title. Here is something more concrete. Let's consider a computer program. And it consists of a very simple loop, just a loop. And here we have some assignment statement. X here just is a vector of variables. So it's not only one variable, several variables. So to this vector of real numbers, there's a function just assigns the values until p does not hold any. So while p does hold, this loop continues. So now, of course, computers cannot calculate with real numbers, but still it's useful to analyze such programs because this can also tell us something about floating point programs, about programs that use integers and so on. How is the function f given, and how is this condition p given? They are just given by expressions. For example, this assignment statement might look like this. We assign to x. We assign to x the value of x squared plus sine y, and we assign to y the value of x plus 2y. This is some sort of parallel assignment which assigns to both variables in parallel new values. And in a similar way, we have an expression that gives this condition, which my function would be inequality while the inequality hold, we move the system. There's just one condition that the set of x that fulfills this condition is compact. So the problem that I want to solve here, I want to prove that such a program always terminates. That it will not just not go for it. Let's look at some visualization of the problem. Okay, thanks for the announcement. So here we have a compact set, the set of x that fulfill the condition. And then we have some values for x, and the program just assigns, according to a function, new values. So we'll get another value, and the loop just continues. It will continue until we arrive at the value that is not in the set. Then we're done. What we want to prove that is that wherever we start, this sequence will finish, it will terminate. After some time we will reach a value that is not in there. Or in other words, if we would have some infinite sequence of assignments, then after some time there's something outside. This is one motivation, and then yesterday I saw the talk for Luke, so I thought I'd have to do something also for ODEs. For ODEs, a similar problem can be started. The difference for ODEs is just now you have continuous time. You don't have one step after the other, but you now move continuously here. And you can study a similar question. Will the ODE for any starting value in the set after some time leave the set? So will any trajectory that you start within the set leave the set after some time? So we want to prove that we cannot stay forever in the set. Or in other words, that eventually we reach something that is not in the set. In the rest of the talk, I will mainly concentrate on this program termination problem, but there are things that I will speak about can also be applied to ODEs with some slight changes. So now, how can one do this? Control people know the notion of the Lyapunov function, and here is something similar to a Lyapunov function. It's not a Lyapunov function, but it gives you similar information. We want to find a continuous function v that behaves as follows. Whenever we have some x that is in the set P, that fulfills the condition that P gives us, and we take one step from x to f of x, then the function will decrease at least by epsilon. So if you look at the picture again, when you take those steps, the function b along those steps will always decrease at least by epsilon. It can decrease more, but not less. This epsilon just has to be a small real number which we can choose. The smaller the easier the thing is. Now, if we can find such a b, then we know that the loop has to terminate. If it would not terminate, if we would stay the set p forever, then the value of b on the x would go to minus infinity. This cannot happen since we are working on a compact set, and so the value of those of b in the set is not bounded from 0.
Excuse me, on your program you work with a differential equation or?
No, now this is for programs.
For programs?
Yeah, yes. But it can be adapted to differential equations.
But after you just have to look at the frontier only.
No. If you look at the frontier only, you could have cycles. You could just cycle forever inside.
Okay, it's okay for you?
No, I want that we leave the set.
Okay.
That's a different question. I want that wherever I start, I will leave the set. So there cannot be cycles.
The problem is that to have a variable trajectories, but to be sure that the constraints will be violated at a certain point.
If I look at the boundary, I can say that it's not possible to leave it if you want. Those things I can say. If I cannot do that, I will leave it.
Yes.
Because from the control point of view, generally we try to prove that the constraint will be not violated a certain amount of time.
Another question is, how can I find such a limit? The approach that I take here is to first choose manually some sort of pattern polynomial, which means I'll say, okay, I think I can find one that has such a form, for example. It will have those monomials, but I will not fix the coefficients. I will just try to look for those coefficients. So the B now has some parameters, and those variables of the computer program or of the OB. And I will try to find values for those parameters such that this constraint holds. So we want to find an A in the concrete examples for those three coefficients, such that for the resulting function b, it has this property that in the set it will always be fixed. So now we are left with this problem. We want to solve such a quantified problem. We want to find some a such that this holds. There's a classical result which says that if everything is polynomial here, so the only operations that we do there is multiplication and addition and inequalities, then this can always be solved. There's an algorithm that can always solve such problems. This is a very nice result and a very important one. The problem is that this is, in one sense, a very theoretical one, because all the algorithms that we can do this have huge complexity. So in practice, using those algorithms, you can only solve quite small problems. There's a famous one called Quantified elimination by cylindrical algebraic computation, and it will not be able to solve problems of practical science. There's also some technique that I worked on in the past using interval branch and bound techniques. I will not go into details, you can find it here, which has some advantages and some disadvantages related to this one, but it also sometimes can solve such problems. But in this talk I would like to speak about a special method that is specially made for problems of this type, that will exploit the program structure that we have there. Now the question is, of course, what could be the structure we could exploit? For this we'll just look at this pattern polynomial. So if you look at this thing, Then on here we have the sum of monomials. This is, the monomials are nonlinear expressions, but the coefficients always occur linear. So it's always some coefficient times something nonlinear. Coefficient times something nonlinear. And this I want to exploit. So it's linear in those parameters. If I would get rid of those nonlinear monomials here, I would have something. So let's look once again at our visualization. Within the set we want to decrease. The first thing is that the set looks complicated. Let's try to reduce to something that is easy for us, and what is easy for us is of course a box. Let's just over-approximate the box. And then now what we want to solve now instead of this problem is just we want to solve the problem that for all x within the box, the v will decrease. So now it also has to decrease here. So you can also write it like this: for all x in this box, the v decreases. We want to find a of this also. And now the next step is to reduce this to linear programming. As I already said, we have expressions in there that look like this. Here it's a little bit more complicated, but roughly it also looks like this. So this looks like this. We have some coefficients. Here those are monomials. The alpha here denotes all the powers that we have in there, and x1 is actually are many variables. So what I will do now is I just take the intervals that are given by this box and substitute it for those monomials here. So if I go back to this thing here, I just substitute intervals for this thing for x1 and x2. The a's are left. After substituting some intervals here, I will have here an interval, due to interval evaluation, here an interval, here an interval. So I will do a1 times an interval, a2 times an interval, a3 times an interval. In other words, I will have an interval linear inequality. So let's do this. General, after substituting intervals here, we have such a linear interval inequality. I just turn around the intervals and write it as a coefficient. So this is a single interval linear inequality. Later we will arrive at a system of linear inequalities, and we will see how, but for now we have just one. So we want to solve this now. We want to find parameters such that this holds, such that for all elements of the intervals the inequality holds. And this can be done. There's algorithms for this, and they are lossless. So there's an algorithm by Krestova which can solve us this. It reduces it to a linear programming problem, and it can solve it. But in the whole process, we might have lost solvability. It might be the case that this is solvable. There is some A that solves this. But due to over-approximation ability, we arrived at a non-solvable linear inequality. So now we have to take care of this. The goal now is to improve the over-approximation. The problem here is that there's some dependency between those elements. If we substitute intervals, we lose the dependency between the first monomial and the second one, and so on. And we want to take care of this. We do it the usual way that interval people do this. Just split. If we have the full box, we lose the information that we include the situation where one monomial is evaluated here, the other one is evaluated there. As soon as we split, we have smaller boxes and the dependency is lessened. And by this, the overapproximation will be smaller. You might also see that then it would be possible to arrive at smaller boxes. Actually, that's what we do, but I will not explain this in detail. For example, when you have this box here, we could take the smaller one, which will be better. This can be done, but I will not explain how precisely we do this. Okay, so how the method works is it takes the box B, splits it into several boxes, and writing this in an abstract way, this just means that from the original constraint, we'll arrive at this conjunction of constraints. Instead of trying to find A that fulfills this, we want to find an A that fulfills this thing, and the first thing has a universal quantified x in B1, and the second one in B2. And then after doing this step of substituting intervals, we'll arrive at an integral system of interval linear inequalities. Which again we can try to solve. And now we can iterate the method, split more of the boxes into further boxes. This arrives, this has as a result more interval linear inequalities, but with smaller coefficients, because the smaller boxes there's less over approximation, and by iterating we will get closer and closer to describing the exact constraint that we had originally. This works, and it works also for some nice examples. Like this one is not for a loop, it's for an ODE. That looks, for example, like this. We might choose such a pattern polynomial, have a set that looks like this, and then we can try to find those coefficients. And this is an example where our implementation found those such coefficients. So to summarize, just as an intermediate step, the main problem was to prove that a certain loop terminates or that an ODE leaves a region. This was done by finding such a function that will always decrease in the region. The method worked by first choosing a pattern polynomial and then reducing the constraint to a system of interval linear inequalities, and then by solving it, finding such an A. If the over-approximation was too big, we'll split the box, arriving at a more precise description of the constraint by interval linear inequalities, and then iterate. There are only manuals that appears choosing this pattern polynomial. This could be also automatized by starting with a small degree pattern polynomial and then iteratively increase the degree. So I have a little bit of time left. So up to now, what I saw up to now is some work that is already quite old. In the last year, I worked with Milan Vladik on improving the splitting heuristics for this method. The problem here was that the splitting here in the naive method was just in equidistant boxes, which is maybe not the best thing to do. The goal is, of course, to do the best splits that we can find. So the problem is this: we have a system of linear interval inequalities that we solved. That was the result of over-approximating the original constraint, and it's not solvable. We cannot find an A. Now we want to try to find out which intervals in this matrix do we have to shrink such that we will arrive in a solvable interval linear system. I will just quickly go through the main idea of how to do this. The first thing is to rewrite this system of interval linear inequalities according to some well-known technique. First, we rewrite this interval matrix in this form of center and radius matrix. Then you can factor out this thing here and write it on the left-hand side. Then you can observe that this holds there is an A such that for all m in this interval this holds if it holds for the maximum here. So instead of writing, we can replace the universal quantifier by this absolute value. And then we'll just choose some A cleverly. We don't explain how. As I said, it cannot be in general the system is not solvable, so it will not be a solution. But we can try to find out how to improve, how to shrink those intervals best. So what we'll do, we have this problem that is equivalent to that problem. We chose an A, then we evaluate both sides, and then we will see which inequality gives us the worst violation of this inequality. And then we choose the split that improves this the most. That's the idea. We have an implementation, some older one for the general method, but also of the splitting heuristics. But unfortunately, I didn't have the time to do some systematic experiments with those splitting heuristics. But for some examples that are tried, the improvement is several times, so let's say 3, 4, 5 times faster. The size of the examples that we compute is up to maybe dimension 6. After that it becomes really difficult. And yes, now I just finished this. Just want to mention that the method works for more general quantified constraints. I just presented it for certain quantified constraints that came from this problem of termination of loops, but the method works for more general constraints. And now we'll conclude with some, not with a kind of traditional conclusion, but with a certain vision, which is maybe science fiction, but the long-term goal that I want to achieve, which is to automatize. Just a joke, of course. Yeah. So in your talk, you described something that was very interesting and I think very useful. But some of the steps you have to do manually. You have to choose these things and so on. Yeah. And I would like to do, sometimes in the future, I want to automatize you and do everything automatically.
There you go.
What does this mean? So, in an abstract way, I want to have automatic, verified, global analysis of dynamical systems. So I spoke about 2 types of dynamical systems. One is computer programs. Maybe it's not at the first point, it's maybe not completely clear that a computer program is also a dynamical system. But in a computer program, you have variables, they have a state. You make steps that change the state of the variable. So a computer program is a discrete time dynamical system. And on the other hand, we have ODEs. We want to analyze them. How do they behave? One thing that you can analyze is, for example, does a computer program always terminate? The analogous calculation for ODEs is, will it, for example, always leave a certain region? Whenever you are in a region, will you leave it? There's also different problems. For example, we calculate invariant sets, which is the problem, maybe the problem that we thought about. Is it the case that when I'm in there, I will never leave it, no matter what I do? So then it suffices to look at the boundary. If on the boundary, all the vector field always looks inside, I cannot leave the set. Both problems are interesting, both for computer programs and for ODEs. For computer programs, this is about avoiding bugs. If you are always staying in a set where you don't have a bug in the computer program, then you're fine. You want to stay in an invariant set where you don't have a bug. And similar thing for ODEs. And for doing this, there are certain types of objects. So today I spoke about this problem, and the object that is useful for solving this problem was this function v, which looks similar to the proof function. Which tells you, okay, if I stay in my set, this function will always decrease, and due to this I have to leave the set. For computing invariants, there's something similar which is called a barrier, which is some hypersurface for which you know that you cannot jump over this surface. So this is not possible.
In control theory, I guess people sometimes talk about semi-permeable surface.
Okay, thanks for this keyboard. I didn't know this. Yes, okay, I have to. And yeah, thanks. So those objects are useful for solving this kind of problems. And both objects, the computation of both objects can be reduced to solving certain quantified constraints. I showed it today for this thing, but also barriers reduced to solving certain quantified constraints. So this is my vision. I want to have solvers that solve those quantified constraints due to this, solve the subproblems, and at the end, maybe in 200 years, somebody will automatize them. Okay, thanks.
I guess we have time for one fast question, if you have some question.
Yeah, so my question is, at the beginning you said that you cannot apply the cylindrical algebraic decomposition because of the huge complexity of this algorithm. But this algorithm works for existential and universal quantifier. And your problem, you have only one quantifier, which is universal, and you have only one inequality. And the algorithm of Collins, or the method of Tarski, says that, of course, it always works and the complexity is really big. But my question is, for such a problem where you have only one inequality and only one quantifier, is the complexity small?
Well, it would be really smaller if there wouldn't be those parameters, because we want to find A such that you have this universal quantifier. So there's results that with the complexity reduces if you have just one quantifier or one block of quantifiers of the same type, but without parameters.
Okay, but if there exists a parameter, the complexity is also doubly exponential?
Well, then you have this amount to one quantifier alternation. So which means that your fixed quantifier, it will still be exponential, and in practice it will be still very difficult. It will not be doubly exponential because there's one fixed quantifier element. But there's also specific techniques that take into account that you have only inequalities. I thought this will not reduce the worst case complexity, but there are methods that work better in practice for such kind of things.
Okay. So, and the second question, maybe, how do you decide the degree of the polynomial V with respect to maybe the degree of P or the degree of F? How can you, do you have bounds about the degree of V?
I don't know. I didn't. It's an interesting question, but I didn't think about this. So.
Okay, and epsilon? How do you choose epsilon?
As small as possible.
Okay.
I have a question. I don't understand why you really need a function V for your problem, because you can, if you perform an interval integration on all your set P of X, you will be able to prove that for all of them you will...
Yes, if you're lucky, yes.
Why if you're lucky?
If you integrate your over approximation gets larger and larger and larger, and as soon as you self-intersect, you might have a loop. You know, you integrate.
Yes, but if your program terminates,
Yes.
then you will have an algorithm which is able to prove it. If it does not terminate, I agree.
Yes.
But if it terminates,
So I agree that this might also work. And I don't know which one will be better.
okay.
There's the problem that if you compute the steps, the over approximation of the reachable states, then you over approximate. And as soon as you reach the over approximation includes states that you already reached before, then you don't know, you have a loop.
Yes, but classically, when you have a loop, okay, but classically you start with a set, and each time you have a box which go out, you reduce your set.
Yes.
And
yeah, but you have this P, okay? You have this box, you compute another box that is reachable after some time, another box, and then it might happen that due to over approximation, the next box overlaps with something that you had before.
Yes. Yes.
Which means that due to over approximation, you have some cycle. It's not in the original system. It's just artificially introduced to the fact that you have to over approximate.
So you have to dissect the first one.
Yeah.
That's what I'm saying. Okay.
Okay, so it's a way to prove that the program is so that's why you try to over-approximate your initial set. To try also to underestimate the way to estimate at what time the program will terminate. It is obvious to do this computation. No need.
That is not obvious to me. I would have to think about this.
And just a comment, because when I talk about semi-permeable surface, it is because in control you introduce controls in the dynamic of the system, and generally one control tries to push your system outside, and the other tries to go inside. And semi-permeable is because only if one control wants to keep the system inside, it's not possible to cross the boundary. Another keyword is similar to boundary.
Okay.
Could be interesting.
Okay.